Hello, and welcome back to our video series on applying Newton's first and second law of motion. Let's take a look at number 6. It describes three masses connected and strung over a pulley. Mass 1 and 2 are connected by a string. Mass 2 and 3 are also connected by a different string. This different string passes over a frictionless pulley. Mass 3 is greater than the combined mass of 1 and 2. Let's take a look. If you have not drawn the picture, please pause the video and do so. Okay, let's take a look at the forces acting on each mass. I'll start with mass 1. Mass 1 has tension pulling up the rope and weight, M1G, pulling down on it. Mass 2 has the same tension, but pulling in the opposite direction. Same rope, same tension. But it also has weight pulling on it, M2G. Since it has a second rope attached to the other end of it, it has another tension going upward. Since we have different ropes, we should clarify these different tensions. For instance, tension 1 and tension 2. To denote that this is rope 1 and this is rope 2. We'll have tension 2 going up on mass 3, as well as its own weight, M3G. We need to draw the free body diagrams for each mass. I'll begin with mass 1. Since mass 1 accelerates upwards, I need to draw tension 1 greater than M1G. The causing force must always be greater and longer than the opposing force. The equation that would model this, if we apply Newton's second law to just this one mass, causing force minus opposing force equals MA, would be tension minus weight equals MA. The force is acting on M2, well, you have the same tension 1, but it's applied in the opposite direction. So I'm going to remove that. Move it down. Going down, you also have weight 2, or M2G. And since mass 2 is also accelerating upwards, you have tension 2. You have to make sure that tension 2 is longer, because it's accelerating upward, than the combined forces of T1 and mass 2G. Since mass 3 has the same tension, we're going to draw tension acting up on mass 3. And to recognize that mass 3 is accelerating downward, we're going to draw weight 3 longer than tension 2. Now, the equation that would satisfy number 2, or mass 2 rather, would be causing force tension 2, this is tension 1, minus, now we have two opposing forces. We're accelerating upwards, we have two opposing forces, tension and weight. So minus tension 1 minus weight 2G, or mass 2G, equals mass 2A, where this is mass 1A. The equation that would model the downward acceleration of M3 would be causing force, M3G, minus the opposing force of tension 2. Tension 2 opposes the direction of acceleration. So minus tension 2 equals M3A. So yes, we can find the equation for each individual mass. However, we want to practice being able to apply Newton's second law for the entire system of masses. Recall how we do this. We're going to use the same equation, causing force minus opposing force equals ma, but this is going to be sigma ma, where sigma m represents the total sum of force. When we do this, recall we are going to neglect any tension that connects two masses. So I'm going to neglect this tension and this tension because they will algebraically cancel. And I will also neglect tension 1 and tension 1. What that leaves us with, ladies and gentlemen, is weight, weight, and weight. Those are the only things that will be causing forces and opposing forces. So let's start with this. A causing force is the weight 3 because it's pointing in the same direction of acceleration. So m3g minus, now we're going to start looking at opposing forces. Since weight 2 is pointing down and acceleration of mass 2 is up, it makes m2g an opposing force minus m1g, which is an opposing force. So I'm subtracting both opposing forces. Equals mass 1 plus mass 2 plus mass 3 times A. This is the equation that models the acceleration of a system of three masses connected and strung over a pulley.